It's all done forever.
So first thing, any questions about any of the homework or anything else? All right. Nothing? All right, what I'm planning on doing is the next step is going over boundary conditions. We talked about forces and torque last time, just briefly, right? Now, I don't spend a lot of time on torque in here or that type of motional stuff. I think you get that in power, don't you? You get rotating machinery problems or not? No? He should do something where he has torque and then he'll do the flex thing, and torque is really something that it's more of a more power related, and you know, torque is really something. Well, if I start there, I'll have to do the whole lecture, but it's usually something. If we have time, I'll go back and cover some of this stuff. It's really more fitting for the power class to do that when they have rotating machinery. Okay, now, what we're going to do now is boundary conditions, all right? So I'm just going to go through this. It's very similar to what you've done before. So for boundary conditions, in the book, and this is on page 259 in the text, they're going to have two regions, 1 and 2, here. And what they're going to do is say that there's a normal component right here that points from region 2 to region 1. In Dr. Wentworth's book, he calls it A21, I believe. And he's saying that that's just a unit vector that points, I think he calls it, yeah, from region 2 to region 1. Region 2 is below it. And here we're going to talk about the boundary conditions. Now, boundary conditions always refer to the tangent or normal component of fields. Remember, when we talk about electrostatic boundary conditions, we talk about E tan 1 was E tan 2. How many remember that? Tangent electric field is the same across the boundary. And what? The normal component of the D field was the same across the boundary, unless there was a charge density on the surface. Do y'all remember that class? I'm going to try. I mean, it's something you're going to have to know for the final for sure. But next thing, so I'll just put this up here. Well, no, I'm going to stick to this. So if we talk about magnetic stuff, if you think about this, this is the way he's going to do it in his book. If you build a little pill box, they call it a pill box, really it's just a cylinder of height h centered about the actual horizontal dividing line, and this has a height h, and it has an area A right there. You know one thing that's true about the B fields in H fields. Well, we know that the integral of B dot ds over closed surface is 0, and the differential formula of this is divergence of B equals 0. How many remember that? What does that imply? There's one very important part that div B equals 0 implies. Think about div D. When we had divergence of D, what was that equal to anyway? Rho V, the volume charge density, right? Volume charge density. Well, think about this. This suggests what? That there could be a magnetic charge density, right? There isn't. Didn't I mention this before? Guys, how many remember me talking about this? Now, I always try to make sure I qualify what I say. In the macroscopic sense, there is no magnetic charge, but supposedly these people, the nuclear physicists, have, when they smash things up on like the CERN super collider thing, they will find for a very short instant in time, and I'm talking like 10 to the minus 12, 10 to the minus 15 seconds, they can separate something that they believe is magnetic charge, plus and minus magnetic charge. It doesn't exist in the normal universe we live in. Do y'all follow me? So I'm just trying to state that so that you will have at least an appreciation for the world we live in, not the world nuclear physicists talk about and do things. I mean, maybe there is something in the universe that has magnetic charge, maybe a black hole or something on the rim of it, but I don't know. Y'all with me, class, on this one? So what this means is that the integral of b dot ds is 0. If you look at this, if we take this and we take the limit as the actual height goes to 0 of this, and we look at the integral of b dot ds over this closed surface, just think about this. We're shrinking the height to 0. Well, that's b dot ds, so it's only going to be the normal component of the b field on either side. Do y'all follow me? So what he suggests is that if you take the b field in region 1, and you go ahead and region 1, dot it with A, make sure A is a surface vector, that plus the B field in region 2, dotted with unit vector A, will be 0. Now I'm going to qualify this. What I'm really doing with that dot product, remember A in general is just the area, but if you think about it as a vector sense or a surface, then it's going to have a magnitude, which is just the area, and it'll have the unit vector direction. Do y'all follow me on that, class? Now what that really does is just get the component of the B field normal, gets rid of the horizontal component. Does that make sense to everybody, class? What this implies and really states is simply that being in normal 1, the normal component of the B field in region 1 is equal to the normal component, I'm not even going to make it a vector, in region 2. That's what it implies. Across this boundary, the normal component of the B field is continuous. All right? Now, if you think about the D field, D normal 1 was D normal 2 if there isn't a surface charge density, right? Well, there is not a magnetic surface charge density, so that's the reason that works perfectly. Do you remember this from physics, anyone? Anyone? Remember these boundary conditions in physics? No? I always wonder about how much retention you have. I assume they talked about it. Physicists are real big on this stuff. Okay, that's the first boundary condition. B normal 1 is B normal 2. Now, if there is no surface current, remember for something like this, you can have a surface current. You can have some K vector. Y'all follow me on this? That would be amps per meter. You can have a surface current. If there is a surface current, it's different. But I'm going to show you the general way things go. If K, the surface current density actually, equals 0, then H tan 1, H tan in region 1 is equal to H tan in region 2. And the way you get that, the way it's done in the book is classic, and I'll put it with the current density. This is the most common. It's rare to have a current density that's not 0, but there are exceptions. I'm going to say that right now. Generally speaking, the surface current density is 0 between materials when you do these problems. But what he's really saying is this. If we just draw something like this, where again we have the height h, and we have a path of length L, parallel to the actual dividing line between the boundaries, if we have that, we're going to have an H field up here, right? Call it H1, and we have an H field down here, H2. I'm just arbitrarily showing this. Now, if we do this, think about this. I'm going to take a path integral, and I'm going to start here at point 1. This is point 2, 3, and 4. I'm going to go around this way. That's my path of integration. Y'all follow me? Well, what I'm going to do is take the limit as h, really as h. This height goes to 0. The integral of h dot dl around a closed loop. What is that always equal to? Integral of h dot dl around a closed loop? Current penetrating, right? I said the current's 0, didn't I? For this part. I said we're assuming no surface current. Y'all follow me, class? So K would be 0, no surface current density. Well, look at this. H dot dl, if you look at this, if h goes to 0, we don't have to worry about any integral effect there. Do you all follow me? You with me, class? You only have to worry from here to here and here to here. Well, what is that really saying? The only component, if I do an integration from here to here, is the tangent component, isn't it, class? And if you go right above there, in the other direction, the only component is the tangent component as well. Do you all see that, class? So, if you look in a book, there's more of a discussion, but what this implies is that the tangent field in region 1 is equal to the tangent field in region 2 if the surface current is actually 0, which is most of the time. There are exceptions. Everybody with me? Do you remember this at all from physics, anyway? No, really? They didn't cover this? Did they not cover it? Didn't they cover E tan 1 as E tan 2? D normal 1, D normal 2? I'm getting concerned. Physicists love this stuff. This is what they live for. They finally can do all the formal math that they've learned to do in their proofs. See, a lot of stuff, you're engineers, right? So you take mathematics and apply it. Physicists do all these things that are basically formal proofs of how, if this is true, and this is true, necessarily the next thing's true, and they're always, in the journal papers, they have that all the time. Anyway, getting back to this, so normally H tan 1 is H tan 2, B normal 1 is B normal 2. Now B normal 1 will always be B normal 2, the normal component. But if there is a surface current density, and this is actually, let me give you the equation for this one. This is equation 4.76 in your book. If you take, do you have your book with you? Write it down if you don't. And he's going to say, if you take A21, that's that unit vector, and you cross it into H vector in region 1 minus H vector in region 2, you actually get the surface current density K. I believe this is in your book. Is it not, class? Anybody have your book to confirm me?
Yeah. Yes, sorry. That's on page 259 in the book.
Okay. Y'all see this? Now here's where this comes from. I'm going to tell you this. If you take a look at this equation right here, and I'll try to make sure I say this. If you take a look at this, and actually this integral form is equal to the integral of curl of H dot ds over the surface that this path integral actually is the perimeter of. Y'all follow me, class? Now, if you look at this right here, if we make the actual height of H go to 0 here, what you really got is a sliver like this. I hope I'm just trying to give you an idea. You don't have to worry about the formal mathematics here, but are you with me on that? If the height goes to 0, you have almost a sliver there, right? Now, this curl itself inside this sliver, because the length won't matter, you can make the length 1. What that'll do is reduce to this equation right here. We could prove it formally. Usually, that's not something we do. And I don't think he does it. Does he do this formally in his book? I doubt it. But he'll have a more general expression. No, he just says the expression. He doesn't prove it. This actually comes from this right here. If you take this and in the limit as the height h goes to 0 and you let L be 1, what you actually find out, that curl equation becomes this. That's all it is. Now, I want to say something. Remember, A21 is a unit vector normal, right? Just hear me on this. So if you take any vector in this direction and you cross it with another vector, what you're really doing is taking the magnitude of this times the magnitude of the tangent component. Y'all follow me? So this cross product is extracting the tangent component of the H field. What this is really saying is H1 tan minus H2 tan is equal to K. And if you just think about that for a second, if you have something like this, right? We're going to let H go to 0 right there. We're worried about either the integral of H dot dl or the integral of curl of H dot ds, right? Y'all with me, class? Well, I mean, these two are equivalent. This and this. By the way, do you know what that's called? The law or the mathematical formulation? Stokes' theorem. That's right, Stokes' theorem. There's a formal proof that people do. You all heard of Stokes' theorem, didn't you, class, or not? You should have in your physics courses, your math courses. But anyway, if you do that, you can either take the limit as the integral of h dot dl. Now remember, there's a surface current K here. So you're going to get K times the length. That would be the current enclosed. And as h goes to 0, you just tangent h field in region 1 minus the tangent of h field in region 2 is equal to K, the surface current. This is the vector statement that takes care of the directional stuff. That's all it is. Okay? He doesn't prove it in his book. If you want a proof, come see me and I'll be happy to do it. It takes a little time to go through Stokes. That form in the limit is as h goes to 0, but it's done. You can just look online if you're interested. You with me, class? Now, I think we should at least do one problem related to this before I give you a whole bunch of homework. So in the book, let's look at problem 448. He says you got a magnetic, or you got two different materials. And here's the problem. Now this is the classic. We're not going to use a current density here, but I'm going to do this, and let me erase a lot of this so I can get it up here and you can appreciate it. Now, I want you to follow me on this. It's important that you see this because this should explain a lot of things. We can do the curl business in a second, or that cross product. If you have region 1 and there is some field, I'm going to give it a B field. Does it say H or B in the book? It's either, it doesn't matter. So if this is region 1, this is region 2. And this has some mu relative 1, this has some mu relative 2 here. You all follow me, class? I'm just trying to show you something. Now what he does is he said, let's use a unit normal. So this is going to be my unit normal. It makes 90-degree angle here. I'm just trying to show you the normal component, right? What he says is up here, we're going to have a vector, and this is going to be, and I'll make it B. It doesn't matter if it's B or H. B1 here, and it makes an angle alpha 1 with a normal component, with an axis that is perpendicular to the plane separated. You all follow me? Now down here, we're going to have, and I'm just trying to show you at this point, right there, that's what that B field is, just on the B1 side. Right below it, there's going to be a B field in region 2. And it makes an angle alpha 2 with the axis. Do you all follow me? Now remember, there's two different regions. Region 2 here, region 1 here. Now we're going to find the actual equation for the B fields that are normal and the B fields that are in the H fields that are tangent in the two things. And we're going to figure out what the angular relation is. You all with me, class? What we're really trying to do is equate the values of the B field on either side and the H field based on the angle. So let's do it this way. You know B normal 1 is B normal 2. Do you agree with that? So B normal 1 is B normal 2. Now what is B normal 1 based on that drawing in the angles? It's what? It's just magnitude of B1 cosine of theta, or of alpha 1, right? You all see this? Take a look. The projection of this B field on the vertical axis right here, that would be B normal 1, is just going to be equal to the cosine of alpha 1 times B1. How many see that? Can you all see it in the back there or not? All right, so I can say that B1, B normal 1 times cosine of alpha 1 What about the normal component over here? And this is just, sorry, this is B1, my bad. This is magnitude of B1. Over here, it's going to be magnitude of B2, right? Vector times cosine of alpha 2. The only thing I'm doing is taking the projection on the vertical axis of the B field in either region. That's it. With me? Now we need the tangent H field. Go ahead.
Is that because it's not, if it were like in the z direction, then you wouldn't have the cosine?
Well, the cosine of 0 would be 1, right? The angle offset would be 0, so cosine of 0 is 1.
So it's like when you're doing the forces, like in physics, like if the force is at an angle, you find the sine and cosine?
Well, yeah, you have to take the projection. It's really the shadow. The easiest way to think about this, I mean, people explain it different ways. If you've got a surface here, you got a vector, and I'll just call it A. Assume the sun is shining here. What's the shadow it makes there? That is the cosine. That's really the cosine of the angular difference between, it's this, angular difference there. It's the shadow it would make. Now, if you think about, that's the horizontal projection right here. If this is angle alpha, it's going to be A cosine. The vertical projection is this. That's going to be just A sine. That's all it is. It's a projection. They call it shadows. Okay? Now, so that's B normal 1 is B normal 2. Now we're going to do, since there is no surface current, H tan 1 is H tan 2. Okay? First, what is the get the B field. What's the tangent component of the B field here? What is this component? I just gave it to you. It's B1 magnitude sine of alpha, isn't it? Alpha 1? So the tangent component of B field would be B1 magnitude times, the sine of alpha 1. Do you agree with that? That's going to be the tangent component of the B field in region 1. Everybody agree? Now that has to be equal to what? Well, B is mu relative 1, I better do it this way. If I take this, remember, that's the tangent component. Well, if I take, and I can say that let me just do it this way. B is mu H, right? Y'all follow me, class? Right? So over here, I've got the B field. I can say that's mu relative 1, mu 0, times H tan in region 1. This component right here is B tangent in region 1. Everybody agree with that? Take a moment. You all agree? I find the tangent component of the B field. Because B and H are related by mu, I find the tangent component of the H field. I'll write it down formally. So I have H tan in region 1 equals magnitude of B1 sine of alpha 1, and then it's going to be over mu relative 1, mu relative 2. Does everybody agree with that? I'm just going through the motions.
Could you explain the tangent wording you're using real quick?
If I have, let me do it over here so everybody can see this. I'll draw it bigger. Suppose I have a vector A. I'm going to just call it a scalar vector A. Now, if this is the angle here, you can see what? That if I want this component right here, right? This is what I'm after right here. This, call it A tan. Right there? Agreed?
Okay.
Well, what is, if I look at this, this would be A normal. So if I have alpha 1 there, right? Now just look. If I want this component, isn't the sine of this? Remember, what is sine going to be? It's going to be opposite over adjacent, right? Equals sine of the angle. Do you all see that, class? Just think about it for a second, logically. This component right here is the same as this component, right? if this was a right triangle, this is a right triangle. Well, if you look at this projection, it's just the sine of alpha. Now just think about it logically. Let alpha go to 0. What's the sine of 0? 0, right? So if this thing's vertically up, right? The projection on the horizontal plane would be 0, correct? What if it's 90 degrees? What's the sine of 90? 1. All of it would be the projection. Y'all see? I'm just trying to show you this. I don't think you'll have a problem seeing it. So that's h tan 1. It's equal to h tan 2. What do you think h tan 2 is based on this one? Yeah.
Where is the
U0. U0, that's my bad. It should be mu0. My bad. Is that what you're calling them, Yana? I am sorry. I apologize. Are you with me? All right, that's h tan 1. What do you think h tan 2 is? Well, the tangent component of this B field would be sine of alpha 2 times magnitude of B2. That would be the component right here. Agreed, class? Then you would have to divide that by mu relative 2, mu0, to get the H field tangent component in that region. Same exact form, so over here you would just say equal to H2 would be magnitude of B2 times sine of alpha 2, and this would be over mu relative 2 mu0. One thing you can see here, I've got normal component here, and I've got tangent component here, right? Now, just take a, do y'all see this, class? I'm just trying to show you. If h tan 1 is h tan 2 and b normal 1, b normal 2, these equations come out. Now, just take a look at this equation for a moment. If you take a look at this, you see you can get rid of mu0? Yes?
This was probably a while back, but how can you say that like the B1, the magnitude of B1 and cosine alpha is going to be equal to like,
Normal?
where's that coming from?
It's back to this drawing. If this is alpha, remember, alpha is with respect to the normal, right? Just watch it. If I wanted the value of this right here, it would be the cosine of alpha, right? Times the magnitude of A, whatever A is, right? That's what I'm doing there. That's all. Just taking projections. Cosine alpha times whatever the value is gives me the actual normal. The sine of alpha times the magnitude gives me the tangent. Did you all follow me this in this class? That's all it is. All right, now, back to this thing. If you look at this, I can get rid of mu0. Do you agree? Okay. Now keep looking. Do you agree I can take this equation, or I basically can take this equation divided by this equation. Now just watch. Do you agree with that, class? Well, it would get rid of B1, would it? If I divide this by that, B1 goes away. Then what do I get? I get sine alpha 1 over cosine alpha 1 divided by mu relative 1. Do you all see that? So I get just sine of alpha 1 over cosine alpha 1, and it's divided by mu relative 1, equal to, divide these two out. I mean, divide that into this, you get rid of B2 magnitude, and then you get sine of alpha 2 over mu relative 2 times cosine of alpha 2. Do you all see what I'm doing? Anything key up on you? Something you can make an even further approximation? Anyway, what is sine over cosine? Trig.
Tangent.
Tangent, that's right. So what I can do is just say tangent of alpha 1 over mu relative 1 is equal to tangent of alpha 2 over mu relative 2. Here's the reason I'm saying that. Instead of going through a long process of getting the projections and then going through the math, if you have a B field here, and you know mu relative 1, mu relative 2 in that angle, you can get the second angle. Y'all with me, class? Basically write that down in your book or in your notes, because this is really nice to know. Y'all follow me, class? And you can go ahead and multiply both sides by mu relative 1, mu relative 2, then get mu relative 2 over here, get mu relative 1. But that's the form that's usually seen first. Everybody, I'm trying to show you some simple things that'll help you. I want to do a problem, if I have time, with numbers. Let's see which one we can do. We can do, it doesn't matter. He does a surface current density, and the next one, I'm going to give you some of these for homework. Let's do 451, the first part. And the reason I'm going to just show you one problem and show you how simple these are. You have to spend time and really understand it in order to do them without a problem, because any type of confusion, you'll mess the whole thing up. All right. So I want to do, this is 451 in the book. Can somebody just tell me what this, we have two regions, right? And really, we can call this the z-axis here. And that means this is the x and y direction. This is region 1. This is region 2. And what else does he say? Mu relative is 4. And free space below. So here we have mu relative is 4. Down here is free space, or mu relative 2 is 1. And he gives us an H field here in region 1. And what is that H field? 3AX, 4AZ. This is a simple one. 3AX plus 4AZ. And there's no surface current density. What he wants to do is find the H field in region 2. I think it's the H field, right? How would you do that? Now, just think about the laws. First, is there a surface current density? No. So it's really what? H10 in region 1 is H10 in region 2. Do you agree with that for starters? Can you all see this problem okay? All right, what's the tangent component of the H field based on this? Now think about it. For z greater than 0, that's the H field. Z less than 0, we don't know. All right, what's the tangent component? What surface is tangent? The xy plane. Correct, class? What's the tangent component? Just look. The x component, right? Y'all agree with that? Let me see your hands. So the tangent component is x. That means H10 in region 1 is 3AX, right? What's the tangent component in region 2? 3AX. That's all you have to say. So that equals H10 in region 2. By the way, any vector at all, is always reducible in terms of the tangent components and the perpendicular components between any two regions. Yeah?
So how do you know that the tangent component is AX?
All right, here's a better question. Suppose this carpet is the XY plane. If I have a vector parallel to that carpet, isn't it tangent, class? That's what the word means. It's in the plane that separates it. That literally is. It's the component that is in the plane. That's 3AX. This is the X component, right? That's it. It is parallel to the XY plane. Can you all see the parallel tangent? Y'all with me, class? All right, if that's the tangent component, what's left?
The y.
Well, the y is 0, is it? All right, so is the normal component. Remember, a vector can be separated into tangent and normal. If you got tangent, normal's what's left. That's all it is. You look here, you see how it's 3AZ? All right, now what did I say for the boundary conditions for the normal component? B normal 1 is B normal 2, right? Y'all with me? So what's the normal component in region 1? The B field now. I have to take that and multiply it by mu. Do y'all follow me, class? Go ahead, Emily. What? All right, I have to multiply by mu to get the B field, right? So that means B normal in region 1 would be equal to mu relative in region 1, I'll put it down, times mu 0 times H normal in region 1. I'm just writing this down. We know mu relative is 4, right? Mu 0. H normal in region 1 is 4AZ times 4, and it'd be AZ. That's equal to the normal component of the B field in region 2. Well, the B field in region 2, in terms of the H field, would be mu relative, which is 1, times mu 0, right? And then it's times the H field that would be normal in region 2. Now if you look at that right here, that means the H normal component in region 2 would simply be equal to 16 mu 0 AZ. And therefore the total H field in region 2 would be made up of the tangent component, which would be 3AX, plus the normal component, which would be 16 mu 0 AZ. Can y'all follow me on how? Yes, sir.
Wouldn't the mu zeros cancel though?
Because
it's
well,
B normal 1 equal to B normal 2?
well, yeah, but you know this. Remember, H will have. You know what? You're right about it. I'm so sorry. That's H, not B. You're right. This that would go away. You're right. I'm sorry about that. Now, can anybody look at the solution? See what does he want the H field? That one or B field? I don't know. 51.
He wants both.
All right. Can anybody just look up? That's the H field. I'm sorry about that. Anybody? It's right. Trust me.
What do you have for?
He wants the
H.
angle for H2.
All right. How do we get the angle into it? Thank you. All right, we got the two components, right? He wants the angle with respect to the normal, or what?
What angle does H2 make with a normal to the surface?
All right, look, here's what he's up to. That's the H field in region 2, right? He wants to know this. He wants to know this angle, alpha 2. Y'all follow me? This would be the H field. I'm trying to show, it's not showing up well, but what I'm trying to show you, if this is the H field here, what angle in region 2, what does it make? What is this angle with the normal? Now just think about it logically. Z is normal, right? X would be parallel or tangent. So if I just draw this up, and I'll do it right here, and I think you're going to see it. Here's what this looks like. I've got 16 AZ. If this is the Z-axis, I've got 16 here, right? This would be the vector component there. And I have 3AX. Call this the X-axis. So I have 3. What he wants is this angle right here. Y'all follow? I'm just drawing it up. I'm trying to separate this thing and blow it up. Y'all with me? What angle is that going to be? Just look at it. What jumps out at you? I mean, I'm trying to show you that this and this are the same, right? This and this are the same. What do you have? Opposite, right? Over, what is that?
Tangent.
Tangent, right. So the tangent of what? Tangent of this alpha 2 is opposite, right? 3 over 16. So what is alpha 2? A10 of 3/16. What is that in degrees, anyone? Say? What? I didn't hear you.
10.6 degrees.
I mean, just, anybody got a calculator you can do it? I know you can read, but I want to just see what's right. Does he show that?
10.62.
10.62 degrees?
That's correct.
10.62 degrees. But you all follow me on this. You have to be able to understand tangent is the same thing as parallel to the surface. Perpendicular is normal. Whatever is perpendicular. Okay? All right. That's that. Now, next, I'll give you some homework problems. We're into the next chapter now, thank God. We're into chapter 5, and this is going to be time-varying magnetic fields. Now here, I'm going to say one thing. Now I'm going to first start off, not like his book does. I'm going to show you the actual set of Maxwell's equations that are valid for time-varying phenomena. Remember, we've done statics. All charges and currents were assumed constant. They didn't vary in time. And that's true to a large extent for simple kind of problems, but in the real world, things vary with time. So, now, this is in the book, but I want you to just write this down. There are two equations called Maxwell's equations that dictate everything. So we have the first one is curl of H is equal to J plus the partial of D with respect to T. These are based on experimental observations. This is simply Ampere's law. Now, what you're used to seeing is curl H is J, right? That's if it's steady state J. There's no time. If you have time variation, you have to add that. That's called the displacement current. How many have heard of displacement current or displacement current density? Remember that in physics? That explains the phenomena that they have observed. This is something that is not real charge flow. I'll get to this in a second. This is actual charge moving through a lattice or through a wire or something like this. This has to do with the density. This is not. I'll get to that in a second. So that's Ampere's law. The next is Michael Faraday's law of induction. He's another real famous guy. So that is curl of E is equal to minus dB dt. Now those are two equations, and the linkage between J, D, B, and E and H are these. D, as you know, is equal to epsilon E. That's always true. J is equal to sigma, the conductivity times E. That's always true. And if you look at this, B is equal to mu H. That's always true. You all follow me, class? I'm trying to just show you this. Let me add one more equation you should know. These you should absolutely know by heart. And its divergence of D is equal to rho V, or divergence of E is equal to rho V over epsilon. All right? And I'm trying to be clear about this. You understand this, class? Those are the equations they are the truth. They are the things we use from which everything else comes from based on assumptions. So if we have these equations, the first thing we're going to do is talk about, well, what does this equation really mean? It's great to write it down, but what does it mean? So we think about charge decay first, and we do this. If I have the curl of H, that equation right there, I take a divergence of both sides. I take divergence of curl of H equal to divergence of J plus d dt divergence of D. Now just take a look. The only thing I've done is take both sides of that equation and I apply the divergence operator. Are you with me, class? All right. Now, next step is important. Yeah.
What? Could you explain the left two equations?
These two?
Yes, I can't really read it.
divergence of D is rho V. That's the only one you need. With me? You can get the second one, D is epsilon E. You can put it in, you can get divergence E is rho over epsilon. You all with me, class? Now,
Do you use the spherical and those equations in the back?
we haven't, you can, these apply in any coordinate system. The divergence, curl, all those operators in the back for the standard Cartesian, spherical, and cylindrical. These equations are independent of coordinate systems. Now back to this. All right, what is this mathematically is zero. This is by definition zero. The divergence of a curl is by definition zero. We can prove that, but I'm just saying. Over here, we have 0 equals divergence of J. Think about this. What is J? Sigma E. I'm going to go through it real quick. So I have divergence of sigma E plus d dt divergence of D. What is divergence of D? Look over there. I just wrote it down. Rho V, right? So this is rho V. The volume charge density. Now what is E?
E is your electromagnetic.
What is the relationship between E and D? So I can say that I have 0 is equal to divergence of sigma, right? And it's going to be over epsilon times D plus the rho V dt. I think you can see where I'm going with this. Now, if both sigma and epsilon are not functions of spatial coordinates at all, if they're constant, you can take that in front. And then you get divergence, or you get really sigma over epsilon, divergence of D plus the rho V dt equals 0. Can everybody follow me what I'm doing here? I simply pull sigma and epsilon out in front because I'm saying they don't spatially vary. If they did spatially vary, then this divergence equation here or here would require additional operations. You'd have other derivatives. But I'm saying they're constant. What is that? That's rho V. So I have sigma over epsilon rho V plus the rho V dt equals 0. How many see that? That's a first order differential equation. Do you all see that? You don't see it?
It's a lot.
Is it dt on the bottom?
Huh?
That's dt on the bottom?
Yeah, it's a time derivative. This is the rho V dt. Okay? Now class, at this point, they usually introduce a constant. They say tau is equal to epsilon over sigma. That's called a time constant. Do you remember in RC circuits you had a tau that was equal to RC? Do you all remember that? Same deal here. Everybody with me? This is a time constant, and it's reflective of how fast charge is actually going to decay if it's introduced in a region. The general solution of this is rho V as a function of time is going to be some constant called rho V0 e to the minus t over tau. I'm going to have to do more on this next time because I literally am out of time. It's in your book. I'll tell you where it is in your book so you can see it. This is on page 287. All right, put it down, page 287. All right. So a logical question that you have is there a quiz on Monday? All right, and here's the way I'm going to approach it. How many want a quiz on Monday? We have a non-majority. How many want to, you're going to get a quiz next week, a Wednesday. How many on Friday? Wednesday has it by unanimous consent. All right, but I want you to do the problems because for me to get through this, I need you to do the problems. If you come in dead, I'm going to go through the next stuff anyway. But you're going to have to know this for on Wednesday. All right, thank you. I hope it helped. Did this lecture make sense?